Electronegativity is the tendency of an atom in a molecule to attract shared electrons to itself. Electronegativity increases as you go left to right across a period and decreases down a group. So the atoms with the highest electronegativity are in the upper right corner of the periodic table, which you can see in this picture here. These are actual electronegativity values, and you can see fluorine is the very highest, followed by oxygen, nitrogen, and chlorine. So atoms in that upper right corner, very, very high electronegativities. You won't be using the actual values, just the general trend. So if I was to rank these in order of increasing electronegativity just based on the trend, sodium would be the lowest electronegativity. Sodium is furthest to the left. And then aluminum, and then sulfur, and then chlorine, and then fluorine. So just following that trend. Electronegativity affects something called bond polarity. So electronegativity is the ability to attract electrons in a covalent bond. So when we're drawing molecules, we tend to draw the shared electrons, the bonding electrons, right in the middle of the two atoms, but that's not actually what happens. The atom with the higher electronegativity attracts those electrons more, pulls those electrons closer to itself. So what's actually happening when I have hydrogen bonded to fluorine, fluorine is the highest electronegativity on the entire periodic table. And so instead of being right in the middle, those electrons that are shared are going to be closer to fluorine than to hydrogen. This creates something called a partial charge. If hydrogen were to completely give its electrons to fluorine, hydrogen would be a +1, fluorine would be a -1. That's not what's happening. They're still being shared. However, they are shared unequally. And so it creates a partial charge where hydrogen isn't a +1, but like a +0.75. And fluorine's not a -1, it's like a -0.75. And you represent a partial charge with this little symbol. Okay, that just indicates that it's a partial charge. There's not an actual value to it. But the stronger the pull, like fluorine's the highest electronegativity, so that's going to be a stronger pull, a bigger partial charge than like if hydrogen was with chlorine. So the stronger the pull, kind of the higher the partial charge. So polarity of a bond is going to depend on electronegativity difference between the atoms. If there is no electronegativity difference, it's called a nonpolar covalent bond. And in that case, the electrons are shared equally. So in a nonpolar bond, there is no electronegativity difference. The electrons are shared perfectly equally. The only time you're really going to see this is with the diatomics, because any other time there is going to be some difference in electronegativity. There's going to be some uneven sharing of electrons. A polar covalent bond is when electrons are shared unequally. And again, I'll write that on the bottom. That creates that partial charge. The electron with the atom with the higher electronegativity is the partially negative atom, and the atom with the lower electronegativity is the partially positive atom. And then finally, you have ionic bonds, where electrons are lost by the less electronegative species and gained by the more electronegative species. So what's important to understand is that this is a continuum. Okay, there's not a hard cutoff for this is what makes something nonpolar versus polar versus ionic. It's a continuum, and as the electronegativity difference between the atoms gets bigger and bigger, the polarity gets stronger and stronger until eventually it's not even polar anymore. Their electrons aren't being shared anymore. The more electronegative species is completely taking the electron from the less electronegative species. So I can rank these bonds in order of increasing polarity. So the bigger the difference, again, the bigger the electronegativity difference, the more polar the bond is going to be. So our least polar bond here is going to be the HH, right? Because there's no electronegativity difference there. That's nonpolar. And then we have to decide between the oxygen, hydrogen, chlorine, hydrogen, sulfur, hydrogen, fluorine, hydrogen bonds. So the next least polar is going to be the sulfur hydrogen bond. Sulfur does not have a super high electronegativity, so it doesn't have a super strong pull on those electrons, so it's not going to be very polar. After sulfur would come chlorine, and then oxygen, and then fluorine. Oxygen is higher than chlorine because chlorine has more shielding, and so as a result of that, it has a lower electronegativity than oxygen. Now, these are all bonded with hydrogen. If they're not bonded with hydrogen, it's a little bit different. What you're looking at really, again, is the electronegativity difference. The further apart atoms are, the bigger the difference is going to be. So if I, let's say I was comparing some fluorine bonds. So I want OF, CF, son of a biscuit, and SIF, and I want to rank those in order of increasing polarity. Actually, accidentally done it in the correct order. So the oxygen fluorine bond would be the least polar because even though those both have very high electronegativities, they're very close to one another. Their electronegativities are very close to one another because they're right next to each other on the periodic table. So there's not going to be a huge difference there. So it would be not a super strong polar bond. The carbon and fluorine are a little bit further apart, so that would be a little bit stronger. And then the silicon and fluorine are the farthest apart, and so that would be the strongest, the most polar bond there.